Hello and welcome folks to a new video. So if you watched my last video, this is the redemption. So if you haven't watched my last video, basically I was trying to create a little setup to demonstrate some control theory stuff, some PID tuning, and it was a bit of a disaster. So you can go and check that out if you really want to, but not a lot happens in it. I just published it as an example of what can happen when you're making things that don't always work out. But anyway, we're back, new video, new machine. This one works, and we're going to use it to demonstrate some PID tuning concepts today. So this guy in front of you might not be immediately obvious what it is, but in a more recognizable form, you would probably recognize it as this guy. So this is an RC servo, and effectively this thing in front of you here with all this electronic brain boxery in the background is also the exact same thing. This is effectively a servo motor. So it's a standard DC motor. It's got some gears. It has an encoder for feedback, and it has an output. It doesn't output to anything, but this is effectively what would be the output of your servo. So servos are kind of an interesting thing. They effectively take a dumb DC motor and they turn it into something smart, whereby you can give it some input and it'll move to some position and it'll stay there. The way it does that is with a PID controller. So that's where we want to work on today. We want to basically use this as a little demo model to tune up a PID controller, with the example obviously being this is the servo, so you set some position, it'll spin to that position and it'll just stay there.
First things first with this project is we have to print all the parts for it, and the parts are pretty simple. There's 4 3D printed parts. There's one big kind of chunky base piece that has a bunch of kind of interesting features on it, which is the main mounting plate for everything. I was going to do like kind of a base thing here, but turned out not to be necessary because the whole thing kind of just stands up on edge when I put all the parts on it. The next piece was to print the gears. The gears are pretty interesting. So printing gears is something I've always been a little bit scared of. Never thought that I'd be able to get the right precision and also making them mesh properly with proper involute profiles. I was able to use Fusion 360's built-in involute gear profile tool, and it was able to make some pretty nice gears with it. I had to tweak some of the settings so that I could get it to actually print at a decent resolution on my printer. If you don't know, I use a 0.8mm nozzle for kind of speed and throughput kind of stuff. Means that fine details are difficult, but I was able to achieve some pretty decent results with these gears, and I'm actually really happy with how they worked. Pro tip if you're printing gears is print them on a raft. So I never print anything on a raft. I didn't even really know it was a thing for a long time when I started 3D printing, but yeah, print your gears on a raft. Rafts aren't necessarily essential for most printing if you have good build plate adhesion, but a gear is the perfect shape that wants to peel off the bed. It's got lots of little tiny corners that all want to just lift up and warp slightly. For a lot of prints, that's not really a problem if you have a tiny bit of warpage on one of your corners, but for the gear, that's obviously pretty critical. You need them all to be nice and flat, so a raft just takes that off, and if you have your settings set up nicely, the gear should just pop straight off the raft if your interface layer is done well. So that's definitely a pro tip. Use a raft if you're printing gears. Last but not least is the assembly. So the whole thing went together really well. This is one of the times where I managed to fully model all the parts of this in Fusion 360 before I printed it all out. So I didn't really have any surprises when I assembled it, but I got all the tolerances just right and everything worked. The gears meshed really nicely. So yeah, it all worked out really nicely, and I'd always love it when you design something mechanically that just all slots together really nicely with the good tolerances. So yeah, that's a pretty big win for this project.
Okay, so we have our gears set up, we have the rig ready. I was going to make a little stand for it, but it seems it actually balances quite nicely on the motor at the back there, just sitting there. So it is a little bit wobbly when I turned it on, but I can figure that out. It works for now, just for a demo. So I've attached a little tape flag onto here, onto what is like the output shaft of this servo. So obviously we've got our big drive gear here. This is the gear that is for the encoder, and then this is the gear for the output. So the output and the encoder have the same ratio to the drive gear, only difference being they'll be spinning in opposite directions. It's kind of like a planetary gear set almost. So yeah, I have it just connected up here to a motor driver. So if I connect this wire to high, we will get a spinning. And there we go. Nothing super crazy here. Yeah, just spins. And it'll spin in the opposite direction as well if I flip those wires around. Yeah, nothing crazy here. It's just demonstration that it is working. The gears actually are working really beautifully. I've never gotten very successful 3D printed gears before. These are probably the best ones ever made, so I'm very happy with those. The ratio is about 2.5 to 1. So this is a 12 RPM motor. So the output shaft should be spinning at full speed at 30 RPM. So it's very slow, but the speed doesn't really matter for this. It's just it needs to have, I wanted to make it a little bit faster. So that's why I kind of reduced that gear ratio a lot. And then also it was convenient to print two gears that are the same, pretty much the exact same, with same gear ratios. But this ratio of 2.5 to 1 gives my encoder a resolution of basically like 200 steps. So if you can imagine that this is like a stepper motor, it's kind of like a 1.8 degree resolution stepper motor, which is like a 200 step stepper. The way I get that is I've got this little encoder has sort of 20 positions inside it. If you read that in quadrature, you can get 80 out of it. And then with the resolution change, because of the gears, you basically can get about 200 steps per revolution or so. So yeah, that's kind of what we're working with, and it's kind of neat numbers that worked out nicely and also give me enough resolution and stuff to work with this. So I got to write code now to make the actual PID loop bit, and then I can give a bit of a demo on that, and then I'm going to talk about the different tuning values and stuff. So stay tuned. All right, so we're going to start with some PID tuning. So to start off with, we'll just talk about some of the numbers and stuff we're going to have for things just to make a bit more sense. We've got our throttle here. So our motor, the throttle value for this is some value between 0 and 255, which is the PWM resolution for the Arduino. So that means that all of the outputs of our PID are going to have to be some values between minus 255 and plus 255. See, 0 being nothing, minus just indicating it's spinning one direction or the other direction. The other things then is we have the output of our encoder up here. So that's going to give us some value. You don't really need to worry exactly what it is, but for our case, it's sort of like integer pulses as the encoder turns around. The exact number for a revolution doesn't really matter. For our demo here, we're going to be using 25 pulses. So it's 25 units of rotation we're going to be targeting to go in each move. So that should tell you then something about how this is going to work. So we need to move about 25 pulses of rotation. So that means that our motor here has to move through, some amount of rotation to make the encoder move that much, which you will then see is the same as the little flag as it spins around on the output shaft. So what we're going to start with is kind of an arbitrarily low value for just our proportional gain. So we have no integral gain, no derivative gain, just a small value for proportional gain. In this case, it's 10. Again, the numbers don't really matter too much. It's just relative to the max, output that we can have, which is 255. It's a relatively small value. So what this will do is this will look at the error at the very start, which is when the error is the largest. It'll see that the error is, so in our case, it's 25. So we start at 0. We want to go to 25. So the error value is 25. So it'll multiply 25 by 10, which happens to give you 250. So that's more or less max throttle at the very start. So what will happen is the motor will start driving at max throttle. And then when the PID loop next hits, it'll check what the error value is. And that error will have gone down. So it'll actually slow down a bit. So what you should see here when I trigger this is that, and you'll see on the right hand side of your screen just here, I'm going to throw up a real-time graph of what the numbers are doing. So you'll see it just sort of very slowly approach the value, and it should just kind of stop at the value, and it'll sort of slow down as it gets there, and you'll be able to see the little flag doing the same thing. So let's hit the button and have a look at that. So yeah, there you have it. We can, well, let's have another look again at that. Yeah, so we started relatively fast and then we kind of slowed down as we got there, and you can see the same thing happening with the graph. It sort of goes up in steps and it sort of curls and tails off towards the top. You'll notice there we have a little bit of error. This is not perfectly lined up. There's some, it's backlash in the gears and things like this. So they're not going to be able to perfectly hit it, but what you're hearing as well, I don't know if you can hear it in the background, there's a little whine, and that's because that small amount of error is telling the motor to drive at an incredibly slow speed that it can't actually drive at, so you get this little ringing whine. Sometimes if you're lucky and you get the encoder to actually land square onto 0, it'll just stop, but it doesn't always happen because of the resolution. But in any case, we kind of were a bit slow there, and we also kind of undershot our target, which neither of those things are ideal. So what we want to do now is we want to sort of arbitrarily increase this gain to see what happens. In this case, the example I'm going to show you is I'm going to up the gain by a lot, and then we're going to have a look at what effect that has. Okay, so this is our next example, and now we have upped our gain a lot. So we went from 10 to 110 now. So let's see what is going to happen now. So you can see we've got some kind of strange behavior went on there. So if I stop this now. Yeah. So what you saw happen there was we accelerated a hell of a lot quicker than we did the last time. But what ended up happening was we ended up in this sort of oscillating state. So what's happening here is we've gone very quickly up to our desired position, but we've then overshot that target and we've started to end up in this sort of back and forth oscillation. So even though we're only overshot by a very small amount, it's enough in this case because we have a much higher gain now with a proportional turn for it to want to then start spinning rapidly in the opposite direction, and then it'll realize it's undershot and then it'll go back and overshoot again, and it'll sort of oscillate like this for a long time. So in this case, it just so happened that it actually slowed down and stopped pretty quickly, which is just happened that it hit a sweet spot, landed at a 0 point, and was happy there. But it won't always do that. Sometimes if you increase this gain more, it would be even worse, and you get more overshoot and higher oscillations out of it. Which, while that may end up being what we call like a stable system response, it might not really be ideal because, especially for our servo motor, we don't want a stable oscillation around the point we set it to. Ideally, we just want it to stop at that point. So let's mess around a little bit more and see if we can't make that better. So we can try some things. We can add some integral gain, we can add some derivative gain, and let's just see what happens to happen then. Okay, so we're going to try and add some integral gain to this to see what happens. So only a small little bit. What we're hoping to see here is that our oscillations, which we kicked off earlier by having a very high proportional gain, we're hoping to see that we can squash them down a little bit and make it come to a more stable, steady state. Now, that doesn't mean that we're going to get rid of the oscillations, but when I click the button, you should see what I mean. So let's go. So we've overshot a little bit, but what's happening now is because we have that steady state gain in there, what it's doing is it's continually looking at what the value is, and it's trying to bring that value to 0. Effectively, it's trying to minimize that steady state error. So this is oscillating, and there we have it. So we've just gotten back to our steady state. So it took a little while, wasn't super fast, but it did get there, and now it's happy to sit there at its value because it was able to oscillate around a little bit, and then it found its set point and it's happy to sit there. But that wasn't really ideal because it was pretty slow. So let's try and make that a little bit faster. Let's try and allow it to overshoot a little bit, and then the whole thing now is that we want to do is we want to squash down how long that steady state error lasts for, to get it to settle a lot faster. This is called your settling time. So let's try and make that better. All right, so we said we wanted to try and reduce that steady state error a little bit. So I've done a couple of things, and we'll have a look at it and see if it's much better. So the first thing I did was I increased the integral gain by quite a lot. So what this means is that for a very small error, like what we saw oscillating around that set point, we're going to have a much larger response, which should make it respond quicker to try and reduce that error. The only thing that can happen here when you do something like this is that now you can have the sort of rapidly changing values, which is something that we don't necessarily want for stability. So what I've done to help with this then is I've added a little bit of derivative gain. So derivative gain is it's sort of the most complicated of all of them in terms of getting it right for tuning. Typically, very, very, very small values is what you need. So in our case, we've introduced an incredibly small value of 0.001. But what it should do is it should respond very quickly to very rapidly changing values. So what that means is that as a value oscillates quickly, this derivative gain should respond in kind of very quickly in the opposite direction to try and dampen it down. So the whole idea here is that we've got our oscillations that have been spun up because of our high proportional gain. We're trying our best to reduce them with a higher integral gain, but that in and of itself also has some oscillations to it. So if we introduce this derivative gain, hopefully that'll squash the whole thing down and we'll get to stability much faster. So with that said, let's click the button and see. So there we go. And that was a lot quicker. So what's really happening there is the little bit of oscillations you're seeing there is more because of kind of errors in that resolution, like I talked about. But what we've seen is we got a little bit of overshoot, then we started to dip back down, we got a small little bit of undershoot, and then we got a couple of very small rapid oscillations, which then very quickly died off to zero, and we got to our stable steady state. So this is, it's a fairly okay system. I mean, it's not ideal. If I had a servo that I had bought that did this, I wouldn't be terribly happy with it. But it is an example of how you are sort of balancing that idea of speed and overshoot and the settling time of a system, and how we can kind of turn those knobs to make it better. So I haven't done a huge amount of like real hard tuning on this. So, it's not perfect by any means, but it does work, and it's reasonably okay at doing it. So if you could tune this system a hell of a lot better to make it better, that's for sure. But in our case, I wouldn't be buying this servo. But that's not the point. The point is just to demonstrate how our tuning values can impact things. But the last thing I want to talk about is that you don't always have to just try and add all these values. Some systems are simple enough that they can be stable with just proportional gain, or sometimes just proportional and integral gain will be enough to stabilize the system. And this system, as it happens, is you can get a pretty decent stable response from it with just proportional gain. So let's just see what values you have to plug in to make that work. Okay, so for our last demo, I have set my proportional gain to 55. You remember we started out with 10, it was kind of slow. Then we went up way up above to about 150, and it was too fast, or 110 I think, and it was too fast. Then we added in some integral gain, we added in some derivative gain to try and stabilize things. We got some overshoot, eventually we got it to settle down, and now at 55, let's just see what happens. I'm fairly certain this will be the best performance we've seen. So that was pretty good. Click it again to get the graph. There we have it. Straight up, no messing around. Just go straight to the thing, and so that's a pretty fast reaction time. Tiny bit of oscillation there, but yeah, that system is working more or less perfectly. That's basically how I would want my servo to respond in real life if I was to buy one of these. Could even reduce that gain a little bit and probably reduce that overshoot even more. Yeah, so there you have it. That's just a really quick kind of example of how you don't need to overcomplicate this stuff either. Always start simple, build it up, only add extra complexity if you need to. It's one of my favorite tenets of engineering. So yeah, I think I'm going to leave it here for this video. I hope you enjoyed it. I hope you got something from it. If you have any questions, leave them down in the comments. I'll do my best to get back to you. So yeah, as always, guys, thanks for watching, and I'll see you in the next one.